Students, today I am here with an interesting and unique microscopic phenomenon in optics, and that is polarization. This phenomenon is unique as it occurs with transverse waves, while others like reflection, refraction, interference, and diffraction are exhibited by both the transverse and longitudinal waves. We know that light is an electromagnetic wave in which electric and magnetic field vectors vary sinusoidally perpendicular to each other as well as perpendicular to the direction of propagation of light wave. So, light wave is transverse wave. In a common source of light like sun, electric bulb, etc., propagation of light in a particular direction consists of many independent waves having planes of vibration randomly oriented, but all perpendicular to the direction of propagation of light. These are known as unpolarized or randomly polarized light. You can see in the diagram 1 the directions of electric field vectors of several waves are perpendicular to the direction of propagation of light wave. Now, a plane or linearly polarized light is that in which electric field vectors are restricted in a single plane. And the phenomenon of restricting the vibrations of light, that is, variation of electric field vectors in a particular direction perpendicular to the direction of propagation of light, is called polarization of light. If we consider the light from a common source to propagate along x-axis, then all electric field vectors can be resolved into two components along y and z directions, so that net electric field can be found along y and z axes separately. And therefore, an unpolarized light can be considered as the superposition of two polarized waves whose planes of vibrations are perpendicular to each other. That can be seen in diagram 2b. In an activity, when an unpolarized light from a common source is allowed to pass through a polarizer P1, we get linearly polarized light with reduced intensity. If now another Polaroid P2 is placed in the path of light and rotated about the axis of light propagation, then in one position the intensity of transmitted light is found to be 0, as shown in diagram 3a. When P2 is rotated by 90 degree from this position, then transmitted light has full intensity same as that on emerging through P1 as shown in the diagram 3b. This activity shows that when the path axes of P1 and P2 are aligned, we get the polarized light on screen, and when the path axes of P1 and P2 are crossed, that is at right angles to each other, then no light is obtained on the screen. So the Polaroid or a polarizer allows only those vibrations which are along its path axis. For intensity of a beam of plain polarized light after passing through a rotable polarizer, there is a law called Melus Law. According to this law, the intensity of polarized light varies as the square of the cosine of the angle through which the analyzer is rotated from the position that gives maximum intensity. That is, I is proportional to cos square theta, or I is equal to I naught cos square theta, where this angle of rotation theta of the analyzer is in fact angle between the path axes of polarizer and analyzer. Polaroid is a material which polarizes light, and it can be used both as polarizer as well as analyzer. As in the activity, P1 acts as polarizer and P2 acts as analyzer. I will explain a little about some of the Polaroids. Tourmaline is a natural Polaroid. Nicole Prism is a Polaroid made of calcite crystal. Quartz is also a Polaroid. In the diagram, you can see a tourmaline crystal with faces cut parallel to its crystallographic axis, AB. It allows only those vibrations which are parallel to AB and others are absorbed. This is the region that transmitted light, which is a plane polarized light, has reduced intensity. In the diagram, also see the plane ABCD is called plane of vibration, in which vibration of polarized light are confined. And the plane KLMN, which is perpendicular to the plane of vibration, is known as plane of polarization. Another Polaroid is Nicole Prism, which consists of two calcite crystals cut at an angle of 68 degree with its principal axis, and their faces are joined by a glue called Canada balsam. The refractive index of Canada balsam is 1.55. When an unpolarized beam of light passes through a calcite crystal, it breaks up into two rays, ordinary ray and extraordinary ray. Ordinary rays have their electric field vectors perpendicular to the principal section of the crystal, and extraordinary rays have their electric field vectors parallel to the principal section of the crystal. For ordinary ray, the refractive index of calcite is 1.658, and that for extraordinary ray it is 1.486. Hence, Canada balsam acts as a rarer medium for ordinary ray and acts as denser medium for extraordinary rays. As a result, the ordinary ray passing through the denser to rarer medium with angle of incidence greater than critical angle, which is equal to 69 degree, undergoes total internal reflection, and hence ordinary rays are not transmitted through the Nicole prism. On the other hand, extraordinary ray passes through the rarer to denser medium and then again to rarer medium. So it is not affected, as the deviation caused in first refraction is compensated by deviation in opposite direction caused by second refraction. Hence, extraordinary rays are transmitted through the Nicole prism undeviated, which is a plane polarized light. Polarized light are also obtained in nature by reflection and scattering. When sunlight is scattered by the dust particles present in the atmosphere, then partially polarized light is obtained, which can be experienced using cameras fitted with polarizing or Polaroid filters. Human eye is not capable of distinguishing between polarized and unpolarized light. In case of polarization by reflection, it was found that when light is reflected by a transparent surface at a certain angle, then reflected ray is polarized. For this, we have a law known as Brewster's law. Brewster's law states that when unpolarized light is incident at polarizing angle IP on an interface separating air from a medium of refractive index mu, then reflected light is fully polarized with vibrations in the perpendicular direction of the plane of incidence, provided mu is equal to tan IP. Polarizing angle IP is also called Brewster's angle. Brewster experimentally found that the reflected and refracted components OB and OC are perpendicular to each other. You can see in the diagram. Angle BOY plus angle COY is equal to 90 degree, or 90 minus IP plus 90 minus r is equal to 90 degree, or 90 minus ip is equal to r. According to Snell's law, mu is equal to sin I by sin r. So here mu is equal to sin ip by sin 90 minus ip, or mu is equal to sin ip by cos ip. So it comes out as mu is equal to tan ip, which is Brewster's law. It says that tangent of the polarizing angle of incidence is equal to the refractive index of the medium. Thus, we see that the polarizing angle depends on the nature of the material of the medium. Let us now see the practical uses of plain polarized light and the Polaroids in our day-to-day life. In cameras and sunglasses, we use optical filters, which are actually Polaroids, and we use them to avoid the glare of light reflected from shiny surfaces like any metallic surface, glass surface, surface of water and ice, etc. These filters cut off most of the light waves, allowing only limited intensity. In cars and other vehicles, Polaroids are fitted in windshields and cover glasses of headlights in such a way that the pass axis of windshield of one vehicle is crossed with the pass axis of headlight covers of the other vehicle. So the glare of the headlights of one vehicle is cut off by the windshield of opposite vehicle while driving during night time. In window panes of aeroplanes also, Polaroid sheets are used to control the intense light to enter inside. Polaroid fitted cameras are used to take pictures of white cloud so that clear and distinct pictures could be obtained by allowing only the light reflected from the clouds and cutting off the partially polarized scattered light present in the atmosphere. To observe very minute objects or particles through microscope, its objective is fitted with Polaroid, which cuts off the glare of light and objects could be seen clearly. Polaroids are also used in holography, that is, in three-dimensional motion pictures. These are also used in calculators and watches. In CD players, polarized laser beams are used as a pointer. We use solar compass for navigation, which is based on polarization of scattered sunlight. For analysis of asymmetries in crystals and molecules, the phenomenon of polarization is used. So these are some of the uses. There are many more which you can try to explore and list up till I come up with some other topic in physics. Good luck.